Morning, everyone. So over the last 2 days, we've been looking at dealing with titration curves. It's just another way of doing a titration, not needing indicators. We basically monitor the pH as we steadily add acid or add base. We noticed that there was a sudden jumping point that was related to the equivalence point here, and we actually saw some of those calculations in yesterday's class. Today, I just want to hint at one of these curves again, but mainly focus on what is that strange buffer region that we've been drawing. Let's just say, for argument's sake here, let's do a weak acid, strong base curve again. Just going to connect it to what we've been learning. If we have, again, we're plotting pH, I'm going to go back to dropping in base, so volume of base added. We're going to have NaOH here in the burette. So there's the NaOH. I'm going to drop it into my unknown concentration of a weak acid, HA. We would have imagined here as a weak acid, right, there's going to be some number of H pluses. As a weak acid, it's not going to start out all that low. That's one thing that they're like asking you. What's some characteristics of this curve here? It doesn't start that low. As you slowly drop in the hydroxide is going to end up killing off the H plus. Now remember the HA, as a weak acid here, it really had trouble forming H plus at the beginning, right? As a weak acid, the Ka is actually really small. I didn't actually produce a lot of H plus. So you drop in hydroxide, it doesn't take much for the hydroxide to have completely killed off the H plus. Fortunately for us, because this is weak, because of the equilibrium, the HA can actually shift to replenish some of the H plus, and then you can add more hydroxide to kill off the H plus. As you steadily kill off the H plus, the acidity here decreases. We'd expect here the pH to climb. At first it climbs suddenly here, but then there's a really strange leveling off region. It's not flat. That's going to be important for today's lesson here. We're going to add in quite a lot of base here, but the pH isn't changing all that suddenly. When the buffer region eventually runs out, that's the region when we actually shoot up and then suddenly go higher. The equivalence point here, again, is going to be the middle of this shooting up region here. Do a mental check for yourself. Can you explain to me why the pH is actually bigger than 7 at equivalence point? Okay. Today, our emphasis here is to focus on what is this buffer region? How did this happen? How is it that I'm adding seemingly quite a lot of base, and yet the pH doesn't change all that suddenly, and yet later on, within a very narrow region of adding base, suddenly the jump is so dramatic? Okay, so we're going to refer to that one there as a buffer region. We actually need to know very little in terms of buffers, but I'm just going to go through more with you here. First thing you want to do is you want to be able to define what is a buffer solution. A buffer is a solution, as we see in that titration curve, is a solution that resists large changes in pH when small amounts of acid or base are added. Okay, so linking it to the titration curve stuff that we did earlier, let's pretend we're right in the middle of our buffer region. Okay, as you add base, we're going to start going to the right. That's like adding hydroxide. As you add hydroxide, I would have expected the pH to suddenly increase like that, and yet, although the pH does climb, it doesn't climb all that suddenly. Now, I know in this experiment, I never actually added in H+, but what you can do here is, if you add H+, that basically undoes some of the base that I added. I would have expected adding H+ would have made the pH jump down really suddenly, and yet the pH, it does drop, but it doesn't drop as quickly. So there's our sort of definition here. Our buffer is able to resist big changes in pH upon a small addition of acid and base. Eventually, when the buffer runs out, yeah, if you keep adding base here, the buffer is totally gone. Yep, then the pH suddenly jumps. The acid as well, yep, suddenly, that's when the pH suddenly jumps. So it's only within a very narrow region. What we're going to need is actually two things. It's going to be a mixture of either a weak acid and the conjugate base, or it's going to be a weak base and its conjugate acid. Those are the two ways we can make a buffer system. A weak acid conjugate base will make what's referred to as an acidic buffer. The other weak base conjugate acid will make what's referred to as a basic buffer. Be really careful with the terminology here. As a buffer, you need to be able to stop pH change upon addition of both acid and base. So an acidic buffer is not just one that can control acid. Buffers in general control both. then what does this acidity part here tell you? Well, the acidic buffer tells you we actually buffer in the pH less than 7 region. So this buffer keeps pHs, let's say I buffer around a pH 5, I can still buffer. You add acid, I keep the pH from dropping all of a sudden. You add base, I keep the pH from increasing all of a sudden, but it buffers in the acidic region. Whereas the other combination here, it buffers, another way of saying that, it buffers in the basic region. But all buffers have to be able to support, control, moderate both the addition of acid and base. Okay, so let's just start off here with a weak acid buffer here. Let's look at CH3COH. Again, anytime you're given a chemical like this, you want to just make sure that this thing here, is it a strong, is it a weak, is it an acid-base salt? Okay, this one here is a weak acid, meaning as a weak acid, this one here is in equilibrium with H plus and CH3COO minus. We have been doing some Ka calculations. The Ka is actually a really tiny number, so that tells you that reactants are favored. Pretty much for all weak acids, most of the concentration actually stays on this side. I'm just going to put some numbers to this here. Roughly, let's say I have 1 molar acetic acid. We're talking so little actually breaks off, totally making up numbers here. You can calculate 0.01, 0.01, okay? Right? It's not that the mole ratio is wrong. For every little bit of this corner that actually breaks off, you get an equal part H plus, equal part acetate. But it's just that the relative amounts here is heavily favoring reactants, okay? So far, this is half of a buffer. So far, we need something to be weak because we're going to see we really need this equilibrium involved here. So far, what I can buffer is I can buffer a base because you can pretend. Let's add a little bit of hydroxide, just like in this titration curve. Who is the hydroxide going to react with? Well, upon adding hydroxide, the OH minus actually neutralizes the H plus in the equilibrium. That's going to end up forming water. So this is going to get tapered off. It's going to create just pure water. As it pertains to the initial equilibrium, however, you're dropping the concentration of H plus. What's the equilibrium going to do? As you drop the H plus, dropping H plus shifts the equilibrium to the right, and therefore, even though the H plus here would drop from the 0.01, because I had so much acetic acid, it's actually able to shift to replenish some of the H plus. It's not going to get it back up to completely, but it's going to try to replenish some of the H plus. As you drop H plus, it shifts the equilibrium right to recreate some of the H plus. The conclusion here is the pH does decrease. The pH does increase. We're getting more basic. pH does increase, but only slightly. Right? That's because you have removed some of the H plus. It regenerated, let's say 90% of the H plus. We have a little bit loss of H plus, but the pH has not changed by much. So far, we're able to buffer base to some extent as long as I have enough acetic acid. But like I said, a buffer needs to be able to buffer both. What if I add H plus at this point? Well, let's work through the Chatelier again here. By adding H plus is directly involved in this expression here. H plus wants to shift the equilibrium to the left. Okay? So you want to add H plus, right? This one goes up. Le Chatelier doesn't like that. I want to shift away from this addition. But if I want to shift away, I actually need to have acetate. Oh shoot, I didn't have a lot of acetate to begin with. So once the acetate is gone, I lose the ability to actually shift to the left. Any addition to H plus will suddenly drop my pH really, really into the acidic region. So H plus wants to shift the equilibrium left, but the acetate, CH3COO minus, concentration is small and runs out. Okay. When the acetate is completely gone, even though I wanted to shift to the left, there's nothing to actually absorb some of the H plus. All that extra H plus is going to make a sudden jump here. So once that happens, all the extra H plus that we have is going to suddenly drops the pH significantly. So by a huge extent, because there's no shifting, there's no getting rid of it. So far, this one here is sort of half a buffer. Buffers needed to be able to control both base and acid. So far, I can control small additions of hydroxide, but I cannot control H+. Well, what was limiting the effectiveness? Limiting the effectiveness was, oh, I ran out of acetate. Is there a way I can actually beef up the acetate concentration so that later on, if you add acid, I can actually shift to the left? Sure. Why not make a mixture here? So far, it wasn't a buffer yet. What if I made a mixture between acetic acid? I know acetate was my conjugate base. What if I mix it in with sodium acetate? Don't get scared away by, oh, where did the sodium come from? An alkali salt is just guaranteed to be soluble. This is just going to beef up the acetate content for me. And now what we're going to have, we had our original equation, Co2. This was in equilibrium with H plus and acetate. At first, our amounts were heavily favored. We had 1 molar acetate, but only very little H plus, very little acetate. Now that I've thrown in a salt, this salt here breaks up, and this salt here beefs up this concentration. Yes, sure, when you actually add in the acetate, it already would be shifting to equilibrium, but I didn't have a lot of H plus, that also wouldn't shift very well. But now that I have sort of good amounts of both, usually we say appreciable amounts, they don't have to be the same. A buffer system needs to have appreciable, there needs to be enough that you can actually appreciate how much is in there. So I need to have appreciable amounts of the conjugate acid, which I had from before with the weak acid, and the conjugate base. So if you then later on, oh, you happen to add acid, oh, I can shift left, I have a ton of acetate. If you add base, it's going to pull down the OH minus, good, I have a lot of acetic acid. Because I'm able to actually shift, that actually is going to moderate the change in H plus. The Chatelier only tries to counteract your change, so it's not perfect. It can't keep the pH absolutely constant, but it's going to keep the pH relatively the same. Okay? So buffer systems here need to have good amounts of both. They don't have to be equal, but they have to be significant on both sides, and that's able to buffer both acid and base. So let's have a look at another mixture here. We also need the thing to be weak. Let me make that note here. We need it weak for equilibrium. If I have something that's strong, it's just a one-way arrow. There is no shifting involved. There's no controlling any additional H+. So those are the two things that you need. You need good amounts of both conjugates, and you need the weak for equilibrium. So would a system of NH3 and NH4Cl, would this one here be a buffer system? Right? Well, let's check it here. NH3 here is a weak base. That's one criteria. Awesome. NH3 here as a weak base. I'm going to write out the complex equation here. This is going to pick up a proton from water, become ammonium, and then form hydroxide. As a weak base, same problem. The Kb is really tiny. You don't actually create a lot of ammonia. You don't create a lot of hydroxide. So far, which way am I able to shift? Because I have a lot of ammonia, you can add H+. If you add H+, it's going to neutralize the OH-. It's going to try to shift the equilibrium to right. Great, I have a lot of ammonia to shift right, no problem. Same problem though, what if I add OH- instead? A buffer needs to be able to do both. If I add hydroxide, sure we are in equilibrium, sure I want to shift to the left, but again, we don't have enough NH4Cl. By adding NH4Cl, it actually solves that problem a little bit here. I'm actually dropping NH4Cl, this dissociates to form NH4+, this is a salt, and I'm going to artificially beef up this NH4+. So that later on, when you add OH-, when you want to shift left, great, I have enough NH4+, I can allow you to shift left, I can moderate how much the hydroxide changes. Okay. So this is the first way, I can just mix these two things together. There is a way to actually have appreciable amounts. Remember in the titration curves, I didn't actually add in any salts. Where did this buffer region actually come from? So the first way of making a buffer is you just mix the conjugate acid with the weak base. Easy as that, right? That's usually the way we're going to do it. The second way is a little bit more complicated. What we're going to do is we're actually going to neutralize the base until we have appreciable amounts. So let me just show you how this looks like on a titration curve. This would be a titration curve here. This time we'll do a curve here, say a weak base, strong acid curve. So I have a weak base in here. As a weak base, I expect the pH here to be fairly high of a value. Let's say this is NH3. NH3 here isn't very good at actually generating NH4+ or OH-. Okay, so heavily reactants favored. I have way more NH3. I don't have much NH4+. I don't have much hydroxide. But what I'm doing here is I'm not just relying on the weak base itself. I'm actually neutralizing some of this NH3. So that's one equation for you to think about. The other equation that's actually happening for the neutralization is actually the NH3 is steadily being killed off by HCl. Well, what's going to happen? The NH3 picks up the proton, that ends up forming NH4. the Cl actually drops off, the Cl minus actually is just spectator, just stays as Cl, you'll notice, although I didn't need to add the salt ammonium chloride separately, just by neutralizing some of the NH3, let's put some numbers to this here. Let's say I had 10 moles of NH3. I would need 10 moles of acid to completely kill it off. Let's say I only was V half. Let's say I only added 5 moles. So therefore, I kill off all the acid. It kills off a little bit of the base. Oh, look. Now I have a situation where I have a good amount of conjugate of the base, and I also have a good amount of the conjugate acid. Even though you didn't see me sneak in any conjugate salt when you weren't looking, by actually neutralizing some of it, sure, it's not as high as it was to begin with, but I have a situation where I have good amounts of both. I'm going to have the ability to actually shift left or shift right. That happens at V half. So back on our curve here, we started off on a really high pH here. We had expected once the buffer runs out, it would shoot downwards and it would go down like this. Basically, that one there would be, I'm going to be volume of acid added here. That's going to be volume A. Halfway, so volume A would have been 10 moles at equivalence. Halfway would hit a situation where I have good amounts of both conjugates. That's going to be V half. And that's actually going to put you right in the middle of a buffer region. If you add acid from that point, it doesn't let the pH drop all that quickly. If you add base from that point, it doesn't let the pOH change all that quickly. So we've naturally produced a system where we actually have appreciable amounts of both chemicals, and that's why for any weak systems, we end up having a buffer system where the pH doesn't change very drastically. Okay, I'm just going to introduce to you 2 common buffers we have in our body, and then we'll end off with a calculation. Turns out for our bodies, the optimum pH for our blood is something like 7.35. Okay, so it's slightly in the basic region. Turns out if our blood pH drops any lower than 7.20, we're going to have a condition called acidosis. Basically, our blood is a little bit too acidic. In this case, we're going to see what happens to the hemoglobin. That could be actually devastating for us. Or if the pH rises too drastically here, it goes to 7.50, we can get a condition called alkalosis, like alkaline. Alkalosis also could be deadly. What I want to just sort of picture here is inside the blood, we actually have a hemoglobin. So hemoglobin equilibrium in the blood. Okay. So this is not even talking about buffer systems just yet. This is just looking at the hemoglobin equation. Hemoglobin is our oxygen carrier. Hemoglobin here will also have an acid form. So let's say HB. That's the acid form of hemoglobin. It's going to combine with oxygen and water. This is an equilibrium in itself. It's going to produce H3O+, and then we have oxyhemoglobin. Oxyhemoglobin is the base form. Okay, so this is just naturally what's happening in our hemoglobin. What normally happens is, here's our body. Okay, we breathe in a bunch of oxygen. Okay, what's going to happen to this equilibrium? Well, with all that fresh supply of oxygen in our lungs, the oxygen content goes up. The acidified form of hemoglobin picks up that oxygen and actually sort of holds the oxygen in this oxyhemoglobin form. It then travels down our sort of circulatory system. Maybe I need to feed the muscles in my foot here. It holds it. By the time it gets to the foot, it then reverses the equilibrium. It then releases off the oxygen that it carried and converts it back into the acid form. So in a condition where we're actually a little bit overly acidic, if we're overly acidic with acidosis, we have too much H+. So if overly acidic, what's the problem with this equilibrium? Well, if I have way too much H+, that shifts the hemoglobin equilibrium to the left, where my acid form hemoglobin was supposed to grab oxygen. Because we're heavily shifting to the left, we're converting any hemoglobin that was carrying oxygen, we're converting it to the form that it can't actually bind to oxygen. So we have a problem for acidosis here. The hemoglobin cannot effectively bind oxygen. So when the blood was traveling around where your lungs are, it's supposed to be picking up all this oxygen. Because this equilibrium is heavily shifting to the left side, the hemoglobin just can't bind with oxygen. it can keep going to your other body systems, but it doesn't have that oxygen to actually replenish your body. The opposite problem here would be true as well. What about alkalosis? Well, hemoglobin would have no problem binding then, right? Well, let's try it. If we are overly acidic, if we are overly alkaline, if we're overly basic, we have a situation where the H plus concentration is really low, right? Acidic would neutralize the H plus. That actually is going to shift the equilibrium to the right. Lo and behold, yes, hemoglobin will have no trouble binding oxygen, but because the equilibrium is shifting to the right, the hemoglobin has bound so tightly to the oxygen, by the time you actually get to your foot where it's supposed to release the oxygen, nope, the bond is being held so tightly, it doesn't want to actually release the oxygen. So what ends up happening, yep, no problem with the binding, but the hemoglobin binds oxygen so tightly, not releasing to the rest of your body. Right. You'll notice that if the optimum pH is 7.3, it doesn't need to get way too acidic or way too basic, and it can already cause problems with this hemoglobin equilibrium. Fortunately for us, there's 2 buffers that help maintain the system. If you, in your diet, you drink a pop or you have something acidic, those are pH 2, pH 3. Without buffer systems, the pH would drop way lower than the 7.20. Fortunately, because we have other buffer systems, we have other equilibrium systems set up, we can actually help to moderate this hemoglobin equilibrium. So I'm just going to hint at these 2 buffer systems in the blood. So 2 common buffers that we have. One buffer is actually a CO2 bicarbonate buffer, HCO3 minus buffer. And that equilibrium here is actually with the carbon dioxide that we actually breathe out, carbon dioxide gas, that's in equilibrium with soluble carbon dioxide. This is dissolved carbon dioxide. After our cells undergo respiration, they end up generating CO2 as a waste product. That CO2 is carried in our bloodstream. This one here ends up in equilibrium, H plus and HCO3 minus, right? So the buffer system has to have appreciable amounts of both conjugates. It has to have appreciable amounts, yet we still have to have a good amount of CO2. We have a good amount to have bicarbonate. So next time you drink a pop, really, really acidic, that's going to have a ton of H plus. That would have dropped your pH really, really drastically. That would have the problem of the hemoglobin can't bind to the oxygen. Whew. Because I have enough HCO3, even though you increase the H plus really, really drastically here, because I'm actually able to shift left, it actually brings the H plus concentration back down. The pH is going to drop, but not by much, okay? What if I encounter something that's basic? Something that's basic was going to pull down my H plus. Fortunately for us, again, we have a good amount of CO2 in the blood. I can shift to the left. I basically want to keep the H plus from changing too drastically because the H plus content will actually change my pH. Anytime, let's say, you're playing sports and you're running around really heavily, sometimes you start hyperventilating, you start breathing out too quickly. What's actually happening there is when you breathe out too quickly, you're actually releasing a lot of CO2. You're losing a lot of CO2 in the system. The CO2 that's dissolved in the blood, so this is dissolved in blood, the CO2 that's dissolved in the blood will shift over and actually replenish some of that CO2. Fortunately, we do have a buffer system. It's not going to actually let the H plus drop too much, but basically, you're losing a lot of CO2 and you're shifting the equilibrium quite drastically over. What the encouragement is if you're hyperventilating, take a paper bag and actually start breathing into a paper bag. Well, what does that do? Well, as you breathe out a lot of CO2. Without the paper bag, the CO2 is just lost in the environment. You're already breathing really heavily. You're having trouble regaining some of the CO2. When you breathe into a closed environment here, all that CO2 is at least stuck in the paper bag. At least when you start breathing in with those heavy gases of air, they're going to be higher concentrations of CO2. They're going to replenish some of that CO2. They're not going to let this shift happen all that quickly. Okay, so that's one buffer system that we have in our blood. There's a lot of backup systems in our body as well. We also have what's referred to as a nutrient buffer. That is a sort of phosphate equilibrium between H2PO4 minus and HPO4 minus 2. We already know the equation. One proton transfer. This is going to be an equilibrium that's set up. Again, how do you recognize that we are a buffer system? We just have to have appreciable amounts of both conjugates. I have to have good amounts of both the weak acid form and the conjugate base form, and that'll also help moderate the pH. So sort of the conclusion out of here, our bodies naturally maintain these two equilibriums so that an equilibrium in the blood here, like hemoglobin, so that it doesn't heavily shift to one side where the hemoglobin can't bind to oxygen, or it binds so strongly that it doesn't release the oxygen. That way our bodies can have this nice interplay between I pick up the oxygen in the lungs, I travel down the bloodstream, I'm releasing off the oxygen to where it needs it, and then I go back and get replenished for oxygen. I need inside my body system both of these equilibrium to happen. One important note here is the pH does change. Right? pH does change, but the nice thing for us is but only slightly. Okay, that's the extent you actually need to know buffer systems. Just for completeness sake here, I want to walk you through an ice table style question. I want to show you, yeah, the pH does change, but comparing with a buffer versus without a buffer. Okay, so this right here is just for comparison's sake. We're going to set up a scary looking ice table. I want you to calculate for me how much does the pH change when 0.30 molar HCl, strong acid, is added to 0.60 molar acetic acid and 0.60 molar acetate. Okay, buffer. Okay, so we do the with buffer situation first. Okay, how do we know this is a buffer? I need to make sure that the thing is weak. So this one here is acetic acid, perfect, weak acid. Chiku. The concentration currently is 0.60 molar. As a weak acid, it does not ionize very well. So we had been saying here, the bulk of it is reactants favored. We don't have a lot of H+, we don't have a lot of acetate. Upon the addition of H+, if I only had the situation, the H+ would go up, I want to shift left, I run an acetate, that's out of luck, the pH is going to drop really, really suddenly. What I've done to make it a buffer system is I've added in the conjugate base. Maybe I added in sodium acetate. By adding sodium acetate here, I beefed up this concentration. The acetate concentration is also 0.60. Again, they don't have to be equal to each other. This is when the buffer is sort of at maximum capacity here. But by doing that, upon the addition of adding 0.30 molar HCl, this one wants to go up. Phew, I have enough acetate, I can end up shifting to the left. What we need to do for this buffer system, it's always a little bit hard to find the pH using H+, because I'm suddenly going to increase it. This one's going to start dropping. For a buffer system, I'm going to cheat a little bit. The Ka value is actually given by hydrogen times acetate times our acetic acid. What I want to find is another way to find pH. I want to be able to calculate the H+ in a different manner. So what I'm going to do is I'm just going to rearrange this expression. So take the acetic acid times the Ka, divide the acetate ion. This is going to give you the H+ content, right? Perfect. If you can somehow figure out what the H+ content is, I would just need to take the negative log of that, and that would end up giving you the pH. Okay. So let's just start it off right now. Before I do any addition, just having my buffer systems, just knowing both of these ones here are 0.6, I can then go, well, 0.60 of my conjugate acid form, it was also 0.60 of my base form. The Ka I can look up on the table. The Ka is actually 1.8 times 10 to the negative 5. The Ka, 1.8 times 10 to the negative 5. This one here is from the table, right? Or could it give to you the problem? This tells me what my starting H+ is. So let's just punch our way through here. Because we happen to have equal amounts here, those canceled out. I know my H+ currently is 1.8 times 10 to the negative 5. That's H+. Let's figure out what the pH is by taking the negative log of this number. Negative log 1.8 e negative 5. That gives me a pH of 4.74. Okay. So if we were on a titration curve here, because this is a weak acid buffer, volume of base added, around a pH of 4.72, we are sort of at a maximum buffer capacity. I'm able to, if you add base, I'm able to keep your pH from climbing all of a sudden. I'm able to keep, if you add acid in this situation, I'm able to keep your pH from dropping all of a sudden. And that's all centered around a pH of 4.74. That's what we call an acidic buffer, because I can control both in the acidic region. Now what I'm going to do is I'm going to do a fancy ice table. We're going to poke at it by adding 0.30. Okay, so let's just rewrite our equation here. CH3COH is in equilibrium with H+. and our acetate, we started off having 0.60 molar, 0.60 molar. I actually know the H plus here is actually this number. I'm just going to say small for now. This is my initial condition. Before I get to my change line, I'm going to just add a line here. This is my stress. I've added in an extra HCl component. HCl is a strong acid. So I think I told you earlier here was 0.30 molar. If I added 0.30 molar HCl, that adds 0.30 molar H plus. I'm basically poking the equilibrium by adding this 0.30. So let's add 0.30 molar of the H plus. The H plus content goes way up. I want to shift to the left. Phew, good thing I have enough of it. What I want to do is I want to get rid of this 0.30. So by shifting to the left, the acetate recombines some of the H plus. I know Le Chatelier here isn't perfect. It can't completely get rid of it, but let's just assume it's perfect. That's actually going to be the change line. If the H plus content needs to come downwards, minus 0.30, the other side has to be a plus, 0.30. Good, I still had enough acetate here. I now have 0.30 of this one. I still have a small amount of H plus, and I have 0.6 plus 0.3. I now have 0.90. Okay. So obviously, because the equilibrium is shifted, the amounts of the conjugates are now different. The pH is now different. Fine. Okay. But from earlier, we had an expression. The H plus is given by the Co times Ka. Let me just write this down for you here. To find the H plus, it's the Ka times the Co divided by the acetate. This formula here is actually a derivation of something called the Henderson-Hasselbach equation. Henderson-Hasselbach. So you want to look into it in a little more detail. I don't need to know what this H plus is, even if it didn't quite completely. So let me just make that note here. Let's assume Le Chatelier completely removes the stress, which we know it doesn't. We learned from chapter 2, it only tries to counteract equilibrium. Even in that case, we're going to see that the pH changes. And all we need to do is we need to take the ratio of the conjugate amounts that we have. So the Ka is still the same, 1.8 times 10 to the negative 5. This time, instead of both of them being 0.6 and canceling out, this time my acetic acid is actually 0.90. The acetate form is 0.30. Let's just punch that into the expression here. 1.8 e negative 5 times 0.9 divided by 0.3 gives me here 5.4 times 10 to the negative 5. Again, just looking at that numerical value here, while earlier the H plus was just 1.8, now it's 5.4, so definitely it's become more acidic. To put this in perspective here, let's calculate the corresponding pH then. The pH is the negative log of this number, so we're going to take negative log of 5.4 e negative 5, and that gives me here pH of 4.27. Okay? Again, I'm not really concerned with what's the starting pH or the ending pH. I'm concerned with the change in pH. You'll notice the pH here has dropped, but the pH has decreased only. The change in pH decreases 4.74 minus 4.27. It's only decreased by 0.47. Remember, pH decreases is a way of saying it's more acidic. Okay? So because of this buffer system, even upon adding a good amount of this HCl, the pH only dropped ever so slightly. On the titration curve here, you've only dropped a little bit. You haven't actually done a sudden jump, as I may have expected. Okay? Just for completeness sake here, I'll let you do this problem here. What if we were without a buffer? Okay? If I didn't have a buffer system here, how much would this addition of 0.30 molar, how much would that change? So what does a system without a buffer look like? Maybe I just have the acetic acid, but I did not artificially beef up the acetate content. So let's start off here. Let's start off with the same 0.60 molar, so an equimolar solution. I want to know how much H plus, how much acetate there is. This is a standard Ka problem. So ice table, I don't know anything about the pH right now. So let's go minus x plus x plus x. So it's 0 and 0 to begin with. I have an x, 0.60 minus x. We're going to make that a simplifying assumption here. Assume 0.0 minus x is basically 0.6. And therefore, we can calculate, given the Ka, H plus with the acetate divided by your acetic acid, we can calculate what the equilibrium concentration H plus there is after dissociating, and we can calculate the starting pH. So, punching our numbers through here, 1.8 times 10 to the negative 5 is equal to x times x. With the assumption, I wrote it down, so I can write this one here as 0.60. the x, which is actually the equilibrium content of H plus, is equal to 1.8 e negative 5 times it by 0.6 with the square root, gives me here 3.2 times 10 to the negative 3. Earlier, the H plus with the buffer system was just a 10 to the negative 5 number. So let's just calculate the corresponding. What is my pH initial right now? Let's take the negative log of this number here. Negative log of this answer, my current pH is actually 2.48. You'll notice this is even before you added the 0.30 molar. This is just plainly, okay, well, we have only the conjugate acid because I don't have this conjugate base. My starting pH is actually way lower. Starting pH, right? Earlier, I had started off at a pH of 4.74. Even after adding the stress, it was only 4.27. And yet, without a buffer, I'm already starting out lower. What's going to happen now is I'm going to add the stress. I'm going to add the H plus, this part here. Let's rewrite the equation. We'll end off with this one. So we have acetic acid, H plus, and we have acetate. So far, based on my amounts, with the assumption, I assume that I basically have 0.60 left over. We have H plus, that's a really tiny number, so that's going to be small to begin with. That's the initial condition here. And now what we're going to do is we're going to stress it out by adding in that same 0.30 molar H plus. So I add 0.30. Although it is in equilibrium, although I do want it to shift left, well, I only have, unfortunately, 3.2 times 10 to the negative 3. That's like 0.003. I have nowhere near enough. When this acetate here runs out, practically all of this H plus is still present. So that's going to be the change line. We're going to have the equilibrium. The equilibrium, because there was no real gains on the left side, so this is going to be 0.60. I wasn't able to get rid of this 0.30, so this 0.30 sort of remains, and then we're just going to end up with acetate is basically going to have run out. We're going to have a small amount that's close to 0. All you're going to do here is, well, if this is the H plus that I added with the HCl, what is the negative log at the end, pH final? The negative log of 0.30. Any guesses? Negative log of 0.3 gives you a pH of 0.522, okay, or 52, right? So first thing we had said, well, the starting pH without the buffer system was already low to begin with. Let's track the change in pH. The difference in pH 2.48 minus this answer, we actually dropped by 1.96 units. And being on a logarithmic scale here, every step is 10 times harder than the one before it. You'd see that without a buffer system, the pH changes quite drastically. All right? So definitely know that a buffer system needs to have appreciable amounts of acid and base. Definitely know that it has to be something that's weak. And I just showed you a calculation for you to practice. Okay? Let me know if you have any problems. Thanks, guys.